Welcome back. So today we'll have two lectures on some aspects of advanced cryptography that's beyond the standard secure communication questions that we talked about the last 2 days. So I called it advanced cryptography for emerging applications. So what do I mean by advanced cryptography? There's a whole space of tools and utilities that have been developed in the cryptography literature since around the 80s. Okay, so it was around 80s that this whole public key revolution happened, and right after that people started realizing that there's much more magic you can do with cryptography. So over time we have a lot of tools, and I've tried to kind of plot some of them here in this kind of informal chart. So going up in this axis, you're going from practical tools or to more theoretical tools, and going from left to right, you're going from things which you are familiar with or likely to be familiar with, so popular tools, and as you go right, things which are not so well known. Okay, so let me show you a few things that you can put here. So of course, what we were talking about in the previous lectures, encryption and authentication, they're very well known and they're really practical. You use it day in and day out. So that's at this bottom left corner. Then there's this whole space of tools of fairly varying degrees of practicality. And they're all useful things, well-motivated things, but not all of them might be equally practical. And not all of them are equally well-known either. A lot of things, even for security practitioners, a lot of these tools are not, even they are not familiar with them. So let me just read out a few names here. Secret sharing is something that's, I would think, fairly well known. We didn't talk about it yesterday. We'll not actually talk about it today either. But it's also, something well known and quite practical. It doesn't need any heavy-duty computation or anything. Then zero-knowledge proofs is a very useful tool, and of late, with the popularity of blockchains, it has become much more popular. So it has come to the left. In terms of practicality, it is fairly practical, not as much as encryption and authentication, but it is how practical it is has been increasing or improving over time recently, once it has become more popular. Right? More popular it becomes, the more people are interested in it and trying to get it to, people are trying to get it to work for everyone interested in it. Identity-based encryption is some advanced notion of encryption. It's not quite suitable for the kind of point-to-point encryption that you would usually associate with when you hear the name encryption, but it still has its own uses. And a similar tool is attribute-based encryption. So in both of these things, there will be some central authority who will be issuing keys, and but the keys are for your identity or for attributes associated with you. And when somebody is encrypting, they encrypt it with some condition, with some policy saying people with these attributes, with these identities should be able to decrypt this message. That's called ciphertext policy, ABE. There's also key policy, ABE, which will say, this is called, there's also key policy, ABE, where you attach attributes on a ciphertext, and the keys will say, which kind of ciphertext can be decrypted easily. Okay? Digital cash, you nowadays hear about central bank digital currency. You hear about e-rupee. They are not cryptocurrencies. They are controlled by the central bank. But as it is usually conceived, they don't have much anonymity, as opposed to when you have banknotes, when you have currency notes, right? They're anonymous in the sense that nobody is tracking who spend this money where, or who you give this money to, cannot be tracked by some central authority. And digital cash is a cryptography concept that's trying to emulate that anonymity property of physical cache. And there is a fairly good solution, but it has been kind of lying dormant for a long time. There's a lot of room for improvement if it has to become practical. Electronic voting, it's clearly a useful thing in this digital world, so that you don't have to go to a voting booth and cast your vote. You could do it from your home. In India, this it's not there is electronic voting or some automated voting machines, right? They're not quite doing electronic voting in the sense that you don't log in from your house and cast a vote. That's very problematic in some sense. Even electronic voting, that's not necessarily what we are talking about. What we are talking about is some form of digital voting, so that it actually gives you, in some sense, better guarantees than paper voting. Everybody can verify that their vote was collected as cast and counted as collected, and you can kind of get a proof that the whole process was done correctly. Okay? Which is not quite the case in paper voting. You don't know if ballot papers were stuffed, ballot boxes were stuffed, or if some ballots were just discarded. You don't have a full track of that. And here again, this is a setting which goes beyond just the digital digital solution. It also involves some, you could say, cyber-physical systems, because it still involves people casting their vote and being able to manually verify it without having their devices and cryptographic software. It should be something a human can verify that their vote was cast, collected as cast and counted as collected. So it's a very interesting solution, but we won't be talking about that either today. Another very, very powerful tool is secure multi-party computation. Okay? And it's a very broad area. In fact, many of these things that are below that could be considered as very special cases of secure multi-party computation with some further restrictions. And we will talk about that a little bit in the next lecture. And finally, another kind of encryption shows up here, fully homomorphic encryption. This is an encryption on which you can compute. So it's also kind of in the flavor of computing on hidden data, and that's same for secure multi-party computation. We'll talk about later. There are also other things I have not included here. There are fancy forms of signatures, things called group signatures and ring signatures, for instance. All sorts of credential systems. And there's a whole lot of tools out here, and some of them, as I said, are more well known. And there are things like secure multi-party computation, which I would think should be more well known, but it's not yet. And partly because it's not that efficient, and you don't get to deploy it everywhere that in principle it could be deployed. But of course, things are changing even as we speak. So this is robust technology, the things that the encryption and authentication, and things in this blue box are what you could call emerging technology. They are there. If you want to build a startup based on any of these things, you could get something going, but not probably yet ready for full-fledged deployment out in the wild. But then there is also these, so things which are not yet, even the theory is evolving. So cryptographers have been working on things, for the last 40 years, creating fancier and fancier things. And some of the latest or more recent things are obfuscation, so software obfuscation. Of course, that's something that has been done forever, but not in a probably secure way. So that is changing to be more principled, formally, probably secure notions of obfuscation. And something called functional encryption, which subsumes notions like identity-based encryption and attribute-based encryption, And it's all about, again, some sort of a computing on encrypted data. But technically, it's much more complicated than fully homomorphic encryption, and also, in some sense, much more powerful than fully homomorphic encryption. So that's things, the evolving theory. And I'm not going to talk about any of that today. Okay, what I'm going to do is just pick a couple of them. So zero-knowledge proofs, secure multi-party computation, a little bit about this digital cache, and go over that in the next 2 lectures. Okay, yeah, so that's what I'm going to do for today. Okay, and try to keep it high level and easy to follow. There'll be a few nuggets of technical detail, so that you get a flavor of of these topics, but you should explore more later. All right, so let me start with zero-knowledge proofs. And before zero-knowledge proofs, I should introduce you to the notion of interactive proofs. Okay, so proof is about convincing somebody of a claim in a way they can verify, right? And that process could be interactive. They could ask you questions, you could give them answers. So that's at a high level the notion of an interactive proof. So you have a prover and a verifier, and the prover wants to convince the verifier that some input that they have, which I'm calling X here, has some property. Okay, so that they ahead of time know what the property is, what the input X is. It's just that prover knows that X has a property, she has additional information about X maybe, and the verifier doesn't. Okay, so technically we talk about X belongs to some language L. Language is just a subset of strings. You would have you've seen that terminology in your theory of computation courses, right? Things like regular languages and so forth. But it's in general just a subset of strings, and you want to prove that X belongs to that subset. These are strings with some property. And okay, so that's the picture. She's saying X is in L, and Bob says, prove it to me. So they run an interactive protocol, and at the end, he should be convinced if X is in the language. Right? That's what we want from it. And this very basic notion of interactive proofs from computational complexity theory considers an all-powerful prover and a computationally bounded verifier. Okay? And this kind of makes sense because if the verifier, why is it that the prover has some more knowledge or some more knowledge than the verifier? Maybe it's because she is computationally unbounded. She can compute things that Bob cannot. And then she has to convince Bob, who should be able to verify it. He is computationally bounded, so he should be able to verify it efficiently, right? So that is the original setting of interactive proofs. This won't be the setting as we move on because this all-powerful prover is not very interesting in real life. In real life, provers will also be computationally bounded, right? Okay, but so what are the formal requirements of an interactive proof system? The first is completeness, namely if indeed X is in L, and then they run. So I'm thinking of somebody's written down a proof system, basically a protocol. Now I'm asking if that proof system has all the desired properties, and the first property is completeness. If it has to be complete, then if you run the proof system as so when I say honest prover, honest verifier, what I mean is that the prover and verifier are running the protocol as we prescribed. Okay? If they run the protocol as we prescribed, at the end of it, the verifier should accept. Okay? That's completeness. So, if you remove completeness, you could have a proof system in which the verifier always rejects, and that would satisfy all the other properties. So we clearly, the whole point of a proof system is so that you can convince a verifier. So that should be possible. But of course, if that were the only requirement, you could have a verifier, a gullible verifier who just says yes. Prover says X is in the language, the verifier says, okay, I accept. That won't be a sound proof system. What is soundness? So soundness says that if X is not in L, then an honest verifier cannot be fooled into accepting a proof where the proof is now given by a malicious player. an arbitrary malicious player, right? So they are not following our protocol. They are doing whatever they want. And we want to make sure that the verifier would reject the proof. Okay? So a little picture here. So this is my adversary in these slides, and rather malicious adversary. And so it's a bad prover claims that X is in L, and whereas it is not. They do the protocol. No matter what the prover tries, the verifier should reject it. Okay? So that's the soundness requirement of a proof system. So let me give an example to make it clear. And this example uses the notion of a prover who is, the story is that the prover has some capabilities that are not available to the verifier. So let me spell that out. So the problem or the claim that the prover is making is about a soft drink, okay? So Coke. And she claims that the soft drink, when it's packaged in a bottle versus when it's packaged in a can, they taste different. Okay? She has superior taste buds, and she can tell this difference. And poor Bob, he drinks them, and they taste the same to him. So he's okay, convince me that you can actually tell the difference. So here's a little natural protocol. If you were to try and do this at home, this is probably how you would do it. So Bob will take a cup, and hidden from Alice, he would pour a little bit of the soft drink into the cup, either from the can or from the bottle. So he tosses a coin, the coin lands heads, then he will pour it from the can, otherwise from the bottle. Okay? And he sends this cup to Alice. So the cup now doesn't carry the label of where the soft drink came from. And her job is to drink it. And if she's telling the truth, she can tell the difference, and she can correctly tell whether it came from the can or bottle. And maybe she got lucky, so you repeat it 100 times. Okay? And if all 100 times she gets it right, then Bob should be fairly convinced that she knows how to tell the difference. Right? She cannot be, or she was lucky in 1 in 2 to the 100 chance, right? There was one correct sequence of answers that was correct, and she managed to get it. If the statement was wrong, the claim she was making was wrong, then what is in this cup is independent of whether it came from can or bottle, and she only has a half chance of getting it right. So to get it right 100 times, she only has a probability 1 over 2 to the 100. Okay, 100 independent trials. All right, so that's a little protocol. Let me change that into a protocol. You might think that's a silly protocol. Who cares about soft drinks? Let's make it into a protocol for a mathematical problem. Okay, and the problem here is graph non-isomorphism. Okay, so what do I mean by that? So graphs, you're familiar with graphs, I assume. Things like this, nodes and edges, and you can represent a graph as a matrix. Like this is adjacency matrix. Okay, so the graph can be represented as a matrix, and in fact, it can be represented as a matrix in different ways, depending on what order you choose for these labels, right? So, one here at the ijth position, ith row, jth column means there is an edge from the ith node to jth node. But the matrix you get depends on how you assign these 1, 2, 3, 4, the numbers to these 4 nodes. Okay. So depending on how you label the nodes, you can get different matrices. So you can go from one matrix to the other by swapping rows and columns the same way. Okay, so you can trust me that these two graphs are for the same. So I'm looking at this. Seems like a slightly older version of my slides, but that should be okay. Okay, so now if I just give you these two matrices, how do you check if they're isomorphic or not? Well, one possibility is to try always to permute, say G0, and see if any of those permutations gives you G1. permute these rows and columns, corresponding to renumbering the nodes, right? But as the graph gets bigger, it's very computationally intensive, and you could hope that there's some better way to do it. And there are many better ways to do it. But as far as we know, we don't have a polynomial time algorithm for it. We have very good heuristics out there. The software you can download and run, and most of the times it works on reasonable sized graphs. But it's still, not a foolproof algorithm. The only foolproof algorithms we know run in super polynomial time. Okay, but this prover, suppose she's able to do that. She can check that these two graphs are not isomorphic. But how can she convince Bob? Well, they can run this protocol, just this same protocol from the previous slide, but now instead of tasting different, what she claims is that the graphs are not isomorphic to each other, right? And the protocol now changes so that earlier you took either the drink from Coke from the bottle or the can and kind of unlabeled it by pouring it into a cup. Here the operation of unlabeling corresponds to applying a random permutation. Okay, so you take this graph G0 and you apply a random permutation. Or imagine you take this graph G1 and apply a random permutation. If G0 and G1 are isomorphic, the result of applying a random permutation to G0 and the result of applying a random permutation to G1 are identically distributed. Okay? Because to go from G0 to G1 is to apply one permutation. A permutation followed by a random permutation is just a random permutation. So, of course, there's a fascinating structure to this permutations. They form a group called the symmetric group, and you should look this up for later. But for our purposes, just enough to be convinced that you apply a permutation, then you apply a random permutation. The whole effect is applying a random permutation. So pi is a random permutation, and pi G0 would be distributed the same way as pi G1 if they are isomorphic to each other. If they're not isomorphic to each other, as Alice claims, then they will be different. Pi G0 will be isomorphic to G0, but not to G1. Okay, they will be coming from two disjoint distributions, pi G0 and pi G1. And so you send this, and Alice can figure out, if as she claims G0 and G1 are not isomorphic, she can figure out whether this G star came from G0 or from G1, and she is supposed to answer that. Okay? And if she gets this right several times, then Bob should be convinced that G0 and G1 are not isomorphic. Otherwise, what's the magic? That's letting her guess it right all the time. So that's an instance of an interactive proof protocol. Now, it was actually an interesting example because graph non-isomorphism, there is no easy way, or there's no obvious ways you could convince somebody that they are not isomorphic. You kind of have to go through. If your claim was that they are isomorphic, you could just show them the isomorphic. If you're now claiming that they're not isomorphic, it seems like you'll have to go through all isomorphisms and make sure they're not good, right? And now with the help of this prover, whom the verifier doesn't trust, the verifier is able to verify efficiently that they are not isomorphic. So it's an interesting example. But let me actually come to another class of problems. They're called NP languages. You might have seen that in your computation, theory of computation or algorithms courses. So what is NP? I mean, this looks like a little bit of notation, but saying something very simple. A language L is said to be in the class NP if, well, one definition is that if there is a non-deterministic polynomial time algorithm for that problem. But another, maybe more intuitive definition is that there is a way to convince somebody that X is in the language, that X has a property, by giving them a witness to that fact. So imagine the question of graph isomorphism, right? So in graph isomorphism, there's an easy way to convince you that X is in the language, that two graphs are isomorphic. A pair of graphs is my X, and looking at it, you may not be able to solve, you may not be able to check if they're isomorphic or not, but if I could tell you the reason why they are the same, then you can quickly verify it. You can verify that you apply this permutation to this graph, you do get the other graph. That's a polynomial time computation. That's an efficient computation. So this R here, the relation, is basically saying that there is an efficient way to take this statement and the witness and run it through a check, and if this check says yes, then you know that X is in the language. Maybe a little more precisely, whenever X is in the language, there exists such a witness. That will convince the verification process. And on the other hand, if X is not in the language, no witness will convince the verification process. Right? It's checking if the given isomorphism maps G0 to G1. If G0 and G1 are not isomorphic, there is no permutation that will map G0 to G1. So if your language, if your problem is in NP, so if Alice were trying to convince Bob that two graphs are isomorphic, what she could do is just send W, right? Send this witness, so send this isomorphism, and Bob can just check if the relation verifies, and he says okay. So basically, this is this is like a trivial situation where this is basically what NP is. NP says that there is a non-interactive proof system. Okay, so we start off by saying interactive proofs, but here it's a very special case of that. It's non-interactive, and further, it's deterministic. The verifier, in particular, doesn't have to toss coins like in the Coke or the graph non-isomorphism protocol, right, where there was some randomness with the verifier. Here, both the prover and the verifier are just deterministic. The prover just sends this witness. That's all good. So NP is in some sense very simple as far as proving things are concerned. However, what if we don't want to reveal this witness? Okay. So in cryptographic settings, often we don't want to reveal the witness. And here is an example. Suppose you have some cryptocurrency. It's for privacy reasons. This cryptocurrency keeps its people's accounts or wallets encrypted in the blockchain. Okay, not how something like Bitcoin works. Everybody knows how much Bitcoins are owned by a particular identity being signature verification key. But there are other blockchain-based cryptocurrencies where you try to keep preserve privacy. Okay? And there, what you would do is something like you have all this, you have your money sitting encrypted. So this A, imagine, is all your money. It says here's how much you have. It's sitting encrypted there. Now you want to take a little bit out of this and give to someone. Okay. So you would split your total amount A into B and C so that you can give B to somebody, keep C with you. But so you create new encryptions of, I'm calling it encryptions, it could be something else, but some sort of something that hides the amount inside. So let's say you have B and C as two pieces that should add up to A, right? If you decrypt the ciphertext B and C, you'll get little b and little c, and your claim is that I didn't create money out of thin air. Originally I had A amount, I still have A amount just sitting in two ciphertexts instead of in one. But how do you convince somebody that you didn't create money out of nowhere? Everybody is trying to ensure that you didn't change anything before your claim is incorporated into the blockchain. Okay, so you claim, okay, these are encryptions such that A equals B plus C, encryptions of A, B, C. And how do you prove this? Well, there's one option, which is you'll just show how these capital A, capital B, capital C were created from little a, little b, little c, and you kind of give the decryption key, everybody can decrypt and convince themselves. Okay. But that's no good because that reveals this a, b, little a, little b, little c. That's what you wanted to hide in the first place, right? So you're worried that you don't trust these verifiers out there. You want to keep your privacy against them. So the question is, could you convince them that A equals B plus C, the numbers inside the encryption, without revealing anything at all about the numbers? Okay? So you want to run this protocol with the verifier, and at the end, maybe the verifier is interested in finding out how much C is, or maybe just checking, is C bigger than this or something, right? They are interested in some information about your secrets, A, B, and C, and you don't want them to learn anything. Okay? And the question is that possible? And that's exactly what zero-knowledge proofs would give you. So the idea of a zero-knowledge proof is it's an interactive proof protocol with further guarantee that the verifier should not gain any knowledge from an honest prover. Except, of course, you are convincing the verifier of some statement, you are claiming that's the case, so they will be convinced of it. So they will learn whether X is in the language or not, but nothing beyond that. Okay, so just to kind of say the same thing from previous slide, but kind of more abstractly. So you want to claim that X is in the language, you have a witness with you. There's a language in NP. And so now we can switch to a setting where the prover is actually computationally bounded. And the reason she knows X is in L and the verifier doesn't is because she has this witness with her. So she can quickly run and she knows that R of XW equals 1. So she has a valid witness. But she wants to convince Bob without revealing to him anything about this witness W. Okay? So we don't know what Bob might be interested in. Some function of W, say, is what he's interested in. We don't want to reveal anything about W. Okay? But how do you formalize this? To say that you don't want to reveal anything about W other than the fact that there exists a W. And it's kind of a philosophical question, but since we are short on time, I'll just jump straight to the answer, and you should convince yourself that this makes sense. By the way, this notion of interactive proofs and zero-knowledge proofs were by Micali and Goldwasser, and actually later Rakoff joined that paper. So the paper is by Goldwasser, Micali, and Rakoff. And it's one of the things that was cited in the Turing Award for Goldwasser and Micali. Okay? So they came with this very interesting notion of what it should mean to say you did not reveal anything or you did not gain any knowledge. And it cannot be information because this proof, this thing here, often would have information about the witness. Not always, but often. So it had to be a definition which which was computational in spirit. And here is, so the definition I'll get to in a second, and the idea is of simulation. But let me first give you an example, and then we'll do the definition. Okay, so the example is of graph isomorphism. Now it is a language in NP. If you didn't care about zero knowledge, there's a trivial way you could prove it. Verify a prover who has a witness could just send it. A witness being the isomorphism. Okay, so there's a setting. There are two graphs, and the witness is some permutation, some way. There could be multiple witnesses, multiple ways you could permute G0 to get G1. But the claim is that there exists some way to permute the labels of G0 so that it looks exactly like G1. And as I said, if you didn't care about zero knowledge, you could just send this permutation. And what is a zero knowledge protocol? So here is a zero knowledge protocol. Okay? So here, it's a randomized protocol. Alice, the prover, first picks a random permutation. Okay, permutation of the labels, right, of the nodes. And she applies it to, say, G1. Gets G star. And she's claiming if they are isomorphic, so and she knows that G star is also a permutation of G0, but for now, the way she obtained G star I have written is by applying a permutation to G1. And yes?
So then they will send the isomorphism for the new graph with G1.
You're suggesting a solution? No, so let me go over the whole thing, okay? So she applies this permutation to G1. She gets a new graph, G star. She sends it to Bob. Okay, so Bob just got this new graph. He has no idea if it's isomorphic to G0, isomorphic to G1, nothing. And he flips a coin, B, and he says, show me that this is actually an isomorphism of G sub B. So if B is 0, he will ask, show me that this G star is an isomorphism of G0. If B is 1, he will say, show me that it's an isomorphism of G1. And sure enough, if B is 1, then, B is 1, then Alice already has a permutation. So what does it mean to show that it's an isomorphism, it's isomorphic to G1? It's to show me a permutation such that G star is, that permutation, say pi star. G star is pi star applied to G1. Well, pi star is just pi. You can just send pi. But if B equal to 0, what should she do? Well, she will set pi star to be pi composed with sigma, which means pi star applied to G0 is pi of sigma of G0. And sigma of G0 is G1. Right? Sigma is the permutation between G0 and G1. So sigma of G0 is G1, so pi of sigma of G0 is pi of G1, which is again G star. Okay? So in either case, what Alice is responding with is a random permutation, pi star, from the point of view of Bob, right? He gets a permutation pi star, he checks if pi star is indeed going to map GB to G star. And then they will repeat this many times. Okay, so maybe she got lucky the first time, right? I picked B equal to 1. Half the time I'll do that. And maybe she got lucky and she could just send pi. But so let me actually, before maybe going further, any questions on the protocol itself? Yeah.
So isomorphism is also in P and non-isomorphism is also in P. So
they're not in P. We don't know they are in P.
Non-isomorphism, what is the witness like in isomorphism?
There is no. So as far as we know, graph non-isomorphism is not in NP. It's in what's called co-NP, meaning graph isomorphism is in NP. So right now I'm giving you a protocol for some language in NP, which is the protocol I gave you for graph non-isomorphism. In some sense, we needed that protocol. We didn't have a better way of convincing you because I didn't have a witness to send you, even if you didn't care about zero knowledge, right? So, again, graph non-isomorphism is not known to be in NP. Graph isomorphism, which is what we are talking about here, is in NP. If you didn't care about secrecy, you could have just sent sigma here. But now that secrecy has zero knowledge, then you could have sent sigma. But now what we are doing is we would either send you pi or pi composed with sigma. If I had sent you both of them, which is probably what you were just asking about in the beginning, show that this G star is isomorphic to both G0 and G1, that would reveal the overall, that would reveal sigma. Right? You can apply pi inverse to this one, compose it with pi inverse, and you'll get sigma back. So it's crucial that Bob is asking that only one of them be shown, that G star is isomorphic to either G0 or G1. And what he sees is just a random permutation. Okay, but let me first ask another question. Why is this sound? Why is this proof system sound? Well, if after she sends this G star, if it were the case that she could have successfully answered for both B equal to 0 and B equal to 1, what does that mean? That means G star is isomorphic to G0 and isomorphic to G1. Well, that means G0 and G1 are isomorphic to each other. Okay, so if she were in a position to answer both values of B, then the statement is true. However, we are not asking her both. We are only finding and asking her to show one of them. And so she could just get lucky, right? But equally, on the flip side, with probability half, she will get caught. She could have maybe picked G star to be isomorphic to one of them, but not both of them, right? If they are not isomorphic. So if they are not isomorphic, there's a probability half that we will ask this bit B in such a way that she cannot answer. So she'll get caught with probability half. If you're going to repeat this 100 times, the probability that she will not get caught means she will not get caught 100 times is half times half times half, and that's 1 by 2 to the 100, and that's a tiny number. Okay, so that's why this is convincing when you repeat this. Why is it zero knowledge? Yeah, let's look at what Bob sees, what the verifier sees. Well, he saw a G star. He saw this bit B, which he picked himself, in fact. And then he saw pi star such that G star is pi star applied to GB. Okay. Now, you might think that, okay, he's learning something, right? He saw G star. He picked a bit B, and he's getting the prover to tell him a pi star such that G star is pi star applied to GB. This is something he couldn't have done by himself. To come up with this, this basically checking that G star and GB are isomorphic, right? And if graph isomorphism is a hard problem, maybe he cannot do it himself. So maybe he's learning something, he's getting some information from Alice by getting Alice to answer this query. However, I'm claiming he's not. Okay, so let's look at his view again. It's a random B, and what is this pi star? I said pi star is going to be a random permutation. If you forget G star for a second, right? Pi star by itself is just a random permutation. It's obtained by picking a random permutation and applying and giving it as it is, or composing it with a fixed permutation sigma. So in either case, it's a random permutation that you're getting. Okay. So but the problem is there's one more thing, G star. So maybe combined G star and pi star is giving you some information. But what's G star? G star is just something you can compute yourself once you know pi star. Okay. So this view, he couldn't have generated in the order in which Alice did it, but he could have generated it himself in a different order. He can pick B and pi star uniformly at random first, and then compute G star. Okay, so everything that he saw is something he could have computed himself in a different order, but he could have just basically sampled what would have happened in the protocol by himself. And that's the idea that he didn't learn anything from this protocol. At the end of the protocol, whatever he saw is something he could have written down himself. So what he's seeing is a probabilistic, there's a distribution over what he's seeing. His view is randomized. He could have sampled a view from the same distribution himself. So there's nothing that's happening in the protocol, or nothing that he got from the protocol that he couldn't have done by himself. And that's why it's zero knowledge. Okay, does that make sense? Okay, so it's a kind of a, in some sense a deep notion, but there's not much to it once you, convince yourself that this makes sense, then there's nothing more to it. So I'll actually go through this a few more times. Okay, so so what is a zero knowledge proof? Just to summarize and to give a definition. First of all, it's an interactive proof that's, to be an interactive proof, it has to be complete and sound. And then it has this property, which now we can formalize, that whatever the verifier sees in a protocol, okay, could be simulated. Verifier, there are two notions of zero knowledge against an honest verifier and zero knowledge against a malicious verifier. They are two slightly different notions. We will stick mostly to zero knowledge against an honest verifier in this lecture. So that will be called an honest verifier zero knowledge. Okay? But that's not the important thing here. Yeah, so, but in this picture, actually, I'm talking about a verifier who could be malicious, who may deviate from the protocol. And further, at the end of the protocol, they may hope to learn something in the protocol, right? Okay, got it. I got some answer that I was looking for. And this is what we don't want to happen, right? Well, we cannot say it won't happen. Maybe it happened because just like we had in the encryption setting, you cannot say the message should be hidden. Maybe the eavesdropper already knew something about the message. You cannot take that away from the eavesdropper. So similarly, maybe the verifier already knew something about the witness, about the graph, by computing himself. You cannot take that away from him. Okay, what we want to say is that he didn't learn anything more. Okay, so okay, so this is all he learned. He said, "Oh, I got some answer," and further, just for good measure, he says, "Here's a transcript. The whole thing I saw. In case I want to come back and recompute things later, that's also I'm putting down as things I learned." But for every such adversarial strategy he might have in the protocol, including he might be malicious, he could be sending messages not as prescribed by the protocol, right, differently. So for every such adversarial strategy, we need a simulation strategy. So you could think of simulation strategy as something we are telling Alice to comfort her that whatever you do in this protocol, you are not giving any information to the verifier other than saying that X is in the language. Okay, so imagine we are telling Alice, imagine you are talking not to this actual verifier, but a simulator, and to that simulator, all you need to say is X is in L. And the simulator can by itself work out a transcript. What happened in the protocol, it would just work it out itself. And clearly in this imagined world, in this simulated world, Alice is not revealing anything to an adversary other than saying X is in L, right? Because that's all she's doing. And everything else is imagined by this adversary. In real world, of course, this is what's happening. Sorry, yeah. And we're saying the outcome of these two views, right? The outcome as in the view of the real protocol, view of the adversary in the real protocol, and the simulated view are the same. Or sometimes we'll say they are computationally indistinguishable from each other. They are not the same, but they are indistinguishable from each other. Okay? That will be computational zero knowledge. Okay? So that is the definition of zero knowledge. I've not put in any math here saying things like negligible difference and so forth. But in English, that's the idea. Any questions on this definition? Okay, so this is a crucial kind of insight that we will be talking about. So remember I said in the beginning, a typical cryptography goal is to preserve secrecy and rather than create secrecy. And this is exactly that going on here. Bob might already know something about the witness, about things in the statement. So we cannot take that away from him. What we can do is say that whatever he learned, he could have anyway learned, even if I just told him that X is in the language, right? So just the claim is all he learns. The fact that the claim is true is all he learns, and there's nothing else that he learns from participating in the protocol. Okay, that should look kind of a mystery, right? Like, okay, so this is a protocol which has zero knowledge. He shouldn't learn anything. Whatever he saw could have been simulated. Then why is this convincing? Why is it convincing that X is actually in the language? Maybe all that is going on was some sort of a simulation. Okay, so kind of to demystify that. Actually, there's not much mystery there, but if it's a philosophical thought, right? How could he have learned anything if the view that he got could have been simulated, even if X is not in the language, right? This simulator maybe could have been run even if X is not in the language. The simulator from our graph isomorphism It picked up B, picked a pi star, and set G star to be pi star of GB. That could be done even if G0 and G1 are not isomorphic, and for 100 such repetitions, right? So that whole view, could have been simulated even if X is not in the language. So why is this proof? Why is getting this view convincing for him? So let me just try to tell you a story to kind of make it less mysterious. And this is, you probably heard this story of William Tell. There's a whole story to it, but the thing you would remember is probably that there was an apple in the head of his son, and he had to shoot an arrow onto the apple, right? And he did that, and won the day. But that's not the story I'm going to tell. So when William Tell is doing all this, we had a little guy Bob watching all this. Okay, so Bob sees this whole thing and says, "Oh wow, William Tell is a great marksman." He goes and tells his friend Charlie. Charlie says, "How do you know?" Okay. "Look, I just saw him shoot an apple, placed it on his son's head, far away, and see this. I got this from the evidence of that happening, right? There's this arrow that went through the apple. Only a great marksman could have done this." And Charlie said, "Look, it's just an apple with an arrow going through it. I could have done it myself. How could this convince you?" But Bob said, "Look, it convinced me because I saw it happening. It may not convince you. Now I show you this apple with the arrow, but I saw the arrow flying through there and hitting that apple. That's what convinced me." So just to kind of show it side by side to what happened in our protocol, Bob comes and tells Charlie, "Hey, G0 and G1 are isomorphic. How do you know?" "Well, Alice just proved it to me. Look, this is what she showed me. She sent me a G star, I asked her B, and she gave me a pi star such that G star is pi star of GB." Charlie says, "Look, anybody could have done this. This B and pi star are random, and G star is just pi star applied to G sub B. Okay, how can that convince you?" "Well, it convinced me because I picked B at random, and she had no trouble answering me at this 100 times. So it's not that she picked the B. If she picked the B and sent it to me, it won't be convincing. But this transcript was generated by this interactive process that convinced me, but it didn't give me any more information, right? Because whatever I saw, I could have sampled it myself. But seeing it happen convinced me." Okay, just to give one more example while we are at it, or one more analogy while we are at it, you might have seen these kind of cartoons. You draw the target around where your arrow hits the wall. So the two scenarios are, you could first draw a bunch of targets at random on a wall, and then shoot arrow, have your king shoot the arrows into the into bullseye in all of them. Versus you could just have the king come and shoot a bunch of random arrows onto the wall, and then have somebody draw painfully targets around it. Okay, and both look the same, both look identical. You don't learn anything, and also the fact that both look identical kind of tells you that you're not learning anything about king's preference about how arrows will be shot or anything, as in how, or rather where arrows will fall. The distribution of the points where the arrows are sticking at the end of both experiments are the same. Okay, if the king is truly shooting things at random, the same distribution with which you are drawing the targets. So in that sense, it's zero knowledge. Both the views look the same. However, it's only one of them that's convincing you that the king can shoot arrows into bullseye, right? That the king is a great marksman. Okay. So this is exactly what we will be doing in our simulations. We will be doing what this little guy is doing here. We will, simulate this transcript, simulate this view, and that's used to say that you didn't learn anything. The fact that you can simulate doesn't really mean If the simulation by itself is not convincing. What's convincing is the soundness is in the protocol only, right? Not by looking at the transcript. Okay, so I hope that kind of demystifies it a little bit. It's not a mystery that you can have protocols which have zero knowledge in them, but the transcripts have zero knowledge in them, yet we're convincing because you saw how it was generated. Okay, so any questions before I move on?